5.2 Characteristic polynomials. Now let's consider the second problem that we are going to address in this chapter. Given an n by n matrix A, how can we find all the eigenvalues of A? By definition, we know lambda is an eigenvalue of A if we can find a non-zero vector so that this homogeneous equation has a solution, has a non-zero solution. And this homogeneous equation has a non-zero solution if and only if this matrix has a rank less than n. This matrix's rank is less than n, so that the null space is a non-zero subspace. And we know the rank of a matrix is less than n if and only if determinant is equal to 0. So now we get the conclusion that lambda is an eigenvalue of A if and only if determinant A minus lambda identity is equal to 0, if and only if this matrix is not invertible. So we define the function fa of t. It is equal to determinant of A minus t identity. And we have the property that lambda 0 is an eigenvalue of A if and only if this function, when it's evaluated at t equal to lambda 0, is equal to 0. So the function has a 0 at the lambda 0. Alright, so we have defined this function of t. It's determinant of this matrix. And this matrix depends on t. But what kind of function is this? Is it an exponential function of t? Is it a polynomial of t? What kind of function is it? As an example, if this is a matrix, then this is fa of t, that's determinant. Fa of t is the determinant of this matrix. So what kind of function is it? Is it a polynomial in t? That's indeed true. How about the degree of such a polynomial? If A is n by n, what is the degree of the polynomial? The degree of this polynomial for an n by n matrix A will be equal to n. We will leave this as an exercise. We call this fa of t the characteristic polynomial of A. And the eigenvalue of A are simply the real roots of this polynomial. And the equation that A minus t identity is equal to 0 is called the characteristic equation of A. For example, this is A matrix, and we would like to find all eigenvalues of A. And we know the eigenvalues of A are the real roots of the characteristic polynomial. So we find the characteristic polynomial. That's the determinant of this matrix that depends on t. And if we take the determinant, we can find the expression to be t plus 3 and t minus 5. So now we have the eigenvalues, minus 3 and 5. Let's try another example. A is this matrix here. And we can see that it's an upper triangular matrix That's the special thing about this matrix. And we would like to find eigenvalues of A. So we find the characteristic polynomial, and it's the determinant of this matrix. We want to take determinant of this matrix. But we know from before that if a matrix is upper triangular, the determinant is easy. Taking the determinant of the matrix is easy. It's simply the product of the diagonal elements. So that's what it is. So now we can find the eigenvalue, -3 and 6. So if we have an upper triangular matrix and we would like to find the eigenvalue, it becomes super easy. The eigenvalue are simply the diagonal entries. Similarly, if we have a lower triangular matrix, the eigenvalues of a lower triangular matrix are also its diagonal entries. In 4.5, we defined similar matrices, and we saw that similar matrices can be viewed as matrix representations of the same linear transformation. Now we are going to look at another property of similar matrices. Suppose we have A and a B, they are similar and they are n by n, and then by definition we know B can be written like this, P inverse AP for some invertible P. FBT is the characteristic polynomial of B. By definition is that B minus Ti identity. Now let's use the fact that we already know. B is equal to P inverse AP. So let's put it in here, P inverse AP. And because there's a P inverse and there's a P, so let's try to have these two terms for here as well. Here we have an identity, but let's replace it with a P inverse P. Well, now what's so great about this? Because now we can pull out P inverse and the P. And right in the middle, we are left with A minus T identity. Now we have the determinant of the product of the three matrices. And we know we can split these three terms into split this determinant into the product of determinant P inverse, determinant P, and the determinant of the middle term. And the ordering doesn't really make a difference because now we are talking about scalar. And what is determinant P inverse, determinant P? Determinant P inverse, determinant P, we know determinant P. Determinant P inverse is equal to 1 over determinant P. So this term is equal to this term, the product is equal to 1. So we are left with this term only. And what is this? This is precisely the characteristic polynomial of A. Voila! We get the conclusion that if A and B are similar matrices, then they have the same characteristic polynomial.